Good morning, everyone. Our speaker today will be Yonatan Gutman from IMPAN, and he will talk about the topological Takens theorem for finitely generated group actions. Please.
Thank you very much. This is joint work with Misha Levin and Tom Meyerovich. So let me state the main theorem. So we have a topological dynamical system, and the point of the main theorem, as I will also explain, I will review the history, is that this is completely general. This is, there is no assumption on G. Of course, this is topological work, X is a compact metric, and so on. Okay, we fix some R. And now we define the following notation. Gxn. These are all X such that the orbit of X has a size less than n. Now we assume that the dimension, I will review it in a moment, Gxn is less than R over 2n. For all n. And this is first assumption. The second assumption is that the space itself is finite dimensional. And in a moment, so when I write dimension, I mean the Lebesgue covering dimension, and I will remind you maybe on that board. Can I use the small board or no?
Yeah.
Okay, so in a moment I will remind you the definition. But under these two assumptions, then for a dense G delta set of continuous functions, so f will be from x to 0, 1 to the power r. So here is where this parameter r appears. We have that the following map, fg, that I will define in a moment. So this is an equivariant embedding. So first let me maybe write the map. So this is what we call sometimes the orbit map. We have an observable from X into the r-dimensional cube. We plot the values of the observable over the whole orbit. And the point is that for a dense G delta set of such functions, this is an equivariant embedding. Okay, now before I state the Haken's version, I want first to remind what is topological dimension. So, so-called covering dimension. Alpha is an open finite cover of X, and then we define its order to be the maximal intersection number. What do I mean by this? At each point, I check how many times this point is in some element of alpha. And there will be some maximum. And I do -1. So for example, here I have a segment. I take this cover. So this is the first open set. This is the second. So as you can see, if I take a point here, it's covered only by one element. Any point here is covered by two elements. Any point here is covered by one element. So this two-set covering has order 1 because it's 2 minus 1. And then the dimension of X is sup of beta, where beta is a refinement sup over all finite open coverings, and here we take, excuse me, I forgot the minimum. So for each alpha we are looking for, we are considering all open covers which refines alpha, and we are trying to minimize the order, and then we take the supremum, and this gives you, it will give you for an interval 1, for a square 2. This is one of the classical notions of dimension that was invented by Lebesgue, and it's not a fractal dimension, so it takes integer value. So it can be 0, it can be infinity also, but it cannot be a fraction.
There are other definitions of topological dimensions. Aren't they all the same for metric spaces?
Yeah, so these covering dimensions have many other ways.
Maybe metric separate.
So actually, I don't know to which definition you're referring to, right? But there is
50 years ago.
large inductive and small inductive is this one, and it was Nagata, I think, even proved it for normal compact, so you don't need metric. The point is, what we will see in this talk is that this definition in some sense is not the good one, and we will use an equivalent definition, but I will get to that later. Which I can already hint to what property this definition doesn't have and which we would like, which is, here we talk about covers, so they intersect each other. And actually in this business what you really want is you want to work with collections of sets which are disjoint, because then it's much easier to perturb, right? If I need to perturb something like this, I have complete freedom, because when I perturb this, it doesn't touch this. So that's why this definition is not the most useful. Okay, now let me now give you the historical background. So first, let us consider the case G is the identity. So in this case, by definition, Gxn, right, for every n, will be the whole space. Do you agree? So in particular, if we have the assumption, we must have dim x, I'm taking n equals 1. Dim x must be less than r over 2, right, by assumption. And then we conclude, the theorem tells us, that for a del G delta set of functions, now notice that when the action is by identity, there is no point to take here, I mean, we just take here the G is the identity, so it's just a map. Okay, I don't know, here I called it big F, here small f, maybe not the best idea. In any case, we know that if we have a compact metric space whose dimension is less than r over 2, it's generic that it's embedded in the r-dimensional cube. And this is referred to, this is a very classical theorem, Menger, Nöbeling theorem. So Menger, this is the famous Menger. He was the advisor and Nöbeling was the PhD student. And I think Menger did it first for dimension 2, and then about 10 years later, Nöbeling generalized it. It's almost 100-year-old theorem.
So, one question. So here, is the existence as difficult as genericity? So somehow once you know that you have an embedding, is it then easy to see that it's generic?
We are using the Bell category theorem framework. So this is a classical case where it comes together. It's hard to me. So I personally, I'm not familiar with the topological category of a case where somebody was able to prove existence without.
So it's kind of morally equivalent.
Yes, right? So it's also, of course, a perturbative argument. So in some cases, it's not constructive. Okay, now let us take the case G equals Z, and let us assume that for all n, the set Gxn is empty. In other words, we are in the so-called aperiodic case. There are no periodic points. Every orbit is infinite. So let us choose r equals 1. Because I guess what I'm trying to say is that in this case, the assumption is for free, right? Because it's an empty set. So I will choose the minimal r, and I get that for a finite dimensional space, for a generic f, this is an embedding. This is called the Jaworski theorem, or Jaworski, excuse me. I mean, I actually met Jaworski, and he pronounces his name Jaworski. So this is from 74.
This is the Canadian Jaworski?
No, he was a PhD student of Auslander, and then he left mathematics, and but I met him in Maryland in 2014. Okay, now let us take the following case. G is still Z, and now let us assume that for all n, the number of points whose period is less or equal than n is finite. This is a very natural assumption. it's more permissive than this. Here we didn't allow. As you can see, the dimension of a finite set is 0. So still we have for free the assumption. So still this theorem tells us that we get the same. And this is called Nerukars. Nerukar. In 91. Okay. In 2016, I just published this theorem in the full generality. So, I don't know, GZ, proven by me in 2016. And then, and I should also note that in some sense, it's not hard to see, or maybe it's hard, but it's known classically, even in the context of the Menger-Nöbeling theorem, that this is sharp or optimal, in the sense that you can construct a space whose dimension is exactly, let's say, R over 2. In this case, we need it to be an integer. And because you have equality here, you show that you are not able to embed it in exactly twice. So you need a little bit more than twice. So already here we see that it's sharp. I think that in retrospect it's very interesting that nobody understood this for so many years. That that actually it's not about finiteness of periodic points; it's about their dimension. Okay, and the last point in the history is the case ZK, which was proven by Ishao, Gabor, Sabo, and myself in 2018. And this was actually, from that moment there was no progress. The reason was that using the techniques that we were using, the more complicated the group became, we were not able to handle the combinatorics. Okay, so now, before I will discuss the proof, let me immediately state another, not less important theorem that you can, with some work, conclude from this. So maybe I will do it here. And this is the topological Takens theorem for finitely generated so assume G is finitely generated, let's say with S generators, then there exists some finite f in G, and we can explicitly bound the size of f. It will be a function of the dimension of x, of R, and of S. So, excuse me, I'm not writing. So, we are exactly in the same setup. We just assumed in addition that G is finitely generated, and then we can find an F finite whose size is bounded by a function which is only a function of the dimension of the space of parameter r, number of generators, such that already, or generically, the following is injective. So the difference is now that instead of sending x to the observable on the whole orbit, we are sending x to the observable only on, how would I say, the finite portion of the orbit generated by this f. Oh, now this is really bad because, okay, let me write like this.
The dependence of the size of the set f, is it explicit? Do you have any, or do you know that there just exists?
I was going to give you the proof, and then you will see the. We choose f as a certain ball, and I tell you exactly how big the ball in the Cayley graph should be for it to work.
Okay.
Which is from this actually it implies that if you know something on the growth of balls, many times people know, then you can, for a specific G, maybe you can improve the general. Because obviously it's easy to give a general bound for the size of n ball in the Cayley graph of a finitely generated group with S generators, but some groups they grow slowly. Slower than the Gauss bound.
And if you apply your proof to the classical Z case, do you get the same size as in the classical Takens theorem, or do you get, or is it difficult to say?
No, I think it's.
Maybe this should be asked after the.
Yes, I believe it's the same, but maybe I'm wrong. Other questions?
Yeah, just to clarify, so you still have the conditions 1 and 2 here?
All the time. All the time I have 1 and 2. So before I give you the historical background for the Takens theorem, let me address a question that I was hoping to get from the audience, but I didn't get, which is, why did you assume G finitely generated? So the reason is that when G is not finitely generated, it's actually easy to construct counterexamples. So I will show you a simple counterexample. It's the space X will look like this. It includes the origin, and it includes concentric circles.
Maybe one more question before you write this. So, theorem has no conclusion. I guess that what you mean is that it is an equivariant embedding.
Yeah. So I hope this is not
Not
equivariant.
equivariant.
Okay. Excuse me. I said it, but I didn't. So G delta dense F is 1 to. Yes. Well, okay. So because X is compact Hausdorff, 1-to-1 immediately tells us that it's an embedding. We cannot. Here there is no meaning to talk about dynamics, right? Okay. So wait a second. So G is F infinity. The free group on infinitely many generators. Actually, you can also take it a Balinization in this. And then the SIs, the SI has radius Ri, I is from 3, 4, and so on. the Ri go to 0, and so in order to make this compact, we also include the 0 point. And it's enough, of course, to specify the action of Gi. So Gi rotates Si by 2 pi over I, and identity otherwise. So as you can see, I claim that Gxn is for any n is a finite union of circles and the origin. In other words, the more you get closer to the origin, because you are rotating in 2 pi over big I, which is, let's say, bigger than this n, then you don't see it for the specific n that you. So you get some, and of course you have a fixed point in the middle. Now, why did I choose here 3? No, because everything here is either of dimension 0, the origin, or of dimension 1. So for r equals 1, I claim I do have right? Because n is bigger or equals to 3. I mean, anything here on the left-hand side you have 1, right? And here you have bigger than 1, so it's okay.
What does it mean otherwise?
Okay, so I said, I defined that the Gi generator, so we have infinite number of generators, and it acts by rotation on the I circle, and as identity on the other one. So it doesn't rotate them. Right? Each generator, I need to specify its action on the whole space. So for example, the G2 will rotate the second circle in 180 degrees, but all other circles it will not move them.
So it is not continuous.
It is continuous, because this is a... They are disjointed. But a very good point. So it's that's the point. We have only these circles that are...
But the Gi is commute, right?
Yes.
So you can take them. That's the point. That's why I said you can take either F infinity or I don't remember, how do you call the one when they are abelian? A infinity? What?
Z infinity.
Now, can somebody tell me why the conclusion of the theorem does not hold in this case, right? In order to finish this counterexample. So maybe let's see. The theorem tells us so let's see. We have the property for all n, and which shows r equals 1. So so I claim that if I so now we take some f finite. So it means that from some I big enough, it doesn't touch. It's the identity. So we are actually in the identity case.
Yeah.
So if we now take an x on this circles that are not touched by F, the Gx has no meaning. Gx is all the time the identity for G in big F. So we basically get a map from X, I mean not from X, let me call it X prime. X prime are these X where the F acts as identity into 0, 1.
Well, several copies of 0, 1. Because you're also allowed to have this.
Yeah, but they are all identical.
Zero identity.
It's a diagonal map, exactly.
Diagonal, okay.
So can a circle be embedded into the language? No. Okay.
That's who's asking.
So this is a counterexample, right? Okay. So now I will discuss the proof of the main theorem.
So in fact, this F should be just a whole G, yes?
Wait.
Kind of
This
have-
was a counterexample.
Yeah. I mean that it shows that even for some infinite here, if you take F maybe infinite but not the whole group, then and it also would work.
You mean, for example, if the complement is finite, then it still doesn't work. So you can take just set of
A
generators.
set of generators, and that would be okay. If you take all the generators.
Okay, so on the set of generators.
You must involve all the generators. That's a correct
Yeah.
statement, yes. Or at least. Again, not quite all, but
But
let's
wait, don't you need the... I mean, for each, you need, I guess, three copies, because you have these circuits and you need to, you will embed them in the, you need 2 copies for each generator. So the G and 2G, let's say, I think it will be enough. But the other combinations are, yes, I think that will be enough. Okay, so now I will discuss the proof of the main theorem. I'm wondering because I don't think I will. Let me ask the audience: what is more interesting, to discuss the proof of the main theorem, or immediately now show how you get the topological Packens theorem from the main theorem? Because maybe this will be more in the direction of your question.
Yes.
Okay, so maybe I'll fast go, because if we start with the main, we will never get there. Okay, so this I will leave on the board. This I will, so maybe here. So as promised. Okay, but in any case, we need the main auxiliary theorem, which is also part of the main theorem. So let me state the auxiliary theorem. And actually the auxiliary, so we can even erase the main theorem. Let F in G, this is not going to be finite. And define. Okay, let P be a partition of F. And now I define xp for all x in x, such that for every g1, g2 in F, g1x equals g2x if and only if pg1 equals pg2. This, if you want, maybe it's easier to think about it with the following terminology. X determines partition P on F. How to think about it? We have the Cayley graph. So let's say this is the origin, S1, I don't know, S2, here maybe S1 minus 1. And now let's act. So, okay, this is some parts of the Cayley graph that represents this finite set F inside G. And let's act with this on X, on a point in the space. So obviously, if the Cayley graph, like here, closes, then of course we know that S1x is the same as S2, I don't know what I want to write here, maybe S2. But the point is that for a specific x, there can be more gluings, right? It's possible, for example, that S minus 1x equals S1x. In other words, when you have a finite set and you have a point x, you can look at the following set, fx, and some points will be identified, some points will not be identified, and this is actually a partition of f. So each x determines a partition. And we want to consider all x which determine a specific partition P. For example, P can be the partition into singletons. If P is the partition into singletons, it means that we are in the case where f, each element in f sends x somewhere else. For example, the group acts aperiodically, so any f will have this property. Okay? And now the assumption. So again, we fix R in and the conclusion for dense G delta and of course I forgot here to say, assume this for all partitions. So the main auxiliary theorem, we are in very good shape for the topological Takens theorem, because the main theorem that we use in order to prove the equivariant version already gives us a set of conditions that if we verify these conditions, we know that this map where we take a finite f is an embedding. Okay, and the difference, if you remember, before we had some condition with those points whose period or whose orbit is less than n, equals than n. Here we have a condition in terms of partitions of f. Notice that f is implicit in the notation. When I write xp, this has no meaning if I haven't fixed an f. So I maybe should have written xfp, but p is a partition of f, so, so it's okay. Okay? So,
but here you have fixed f or
yes.
okay.
But the point is,
Yeah.
not every f will have such nice properties. In order for this to be proved, you need to check this. Okay? So, so I want to discuss, of course, okay, so going from the main auxiliary theorem to the main theorem is not so hard, and maybe this is also not your question. This is the point where you use the fact that X is finite dimensional. Because notice that in this theorem, we do not assume X is finite dimensional. Okay? But I guess it follows, I mean, you get it from the conclusion, but you don't assume it. Okay, so maybe I should say, so when you use the main auxiliary theorem in order to get the main theorem, you apply it on x, gxn, not on x.
So just one question to understand. So if your partition is, what happens? Okay, so your partition is just into singletons.
Yes.
And not all you're saying is that your map is, well, one-to-one on F, so to speak, for a given X. Right? I'm just thinking the partition is
Okay.
into singletons. Then the second condition happens even when G1 is equal to G2. So essentially then you say that on this F piece of an orbit you are...
No, but wait, isn't in that case X is xp? If we know that for all x, the x determines a partition of singleton.
I'm kind of slower. I'm a bit slower. I'm just trying to understand what is xp. If p is a partition into singletons. And is this understanding...
Could you repeat again? What
so
is...
Okay, so we have F. We fix P. Okay, so we fix P to be a partition into singletons, the trivial one, right?
But okay, but I just want to again say that the assumption is for all partitions.
Sure.
So there is no
I
such
understand
thing.
it, but
Okay.
let me understand why. Before I understand all.
So you are now taking a specific partition.
Yes.
So okay, so what is XP?
So then XP is just these guys such that evolutions and the elements of F take different values.
Correct.
Right.
This might be a big set, a small set, it might be empty, or it might be everything.
And we want to say that its dimension is not too big.
Yes. But in order to conclude this, it's not enough to consider one partition, you need to consider all partitions.
So what happens if I take the singleton partition, not partition into singletons?
So that would correspond to X such that are fixed by all elements of F.
Okay. Yeah.
So that's the F fixed, I guess. Yes?
But so if you take all possible partitions B, then you obtain a partition of X into this subset XP, because for each X you have only one partition P, right?
Exactly.
So,
Absolutely. Correct. Correct.
yeah.
And so yeah, so I think this, thinking like Artem, you start thinking, how would I try to prove this? Right? Okay, now I wanted to get the topological Takens theorem from the main auxiliary theorem. So so it is enough to find f which satisfies the theorem, which satisfy the main auxiliary theorem. Okay, so let us just denote, let D be the dimension of X on the right hand side. And we need to verify so I claim okay, so no wait, it's too early, so I'll take now M which is bigger than 2D over R and is an integer, and F will be Bm0 in the Cayley graph on S generators. Why did I make this choice M bigger than 2DR? I claim that if P has more than 2D over R elements, then the star holds automatically. Why? No, because in that case, notice that when I enter on the right hand side P, I get something bigger than D. Now everything in my space is small or equal, so it's automatic. So we need only to do the case. Okay, so here the number of generators enters here. This is the M ball in the Cayley graph. And because you know the number of generators, you can bound the number of elements in a BM ball around the identity in the Cayley graph.
What is R?
R is this parameter that we fix always in the beginning and appears in the 0, 1 to the power R to the power F.
The dimension of the target space.
Of the alphabet.
Yeah.
Because it's alphabet to the power F.
So now you assume. So what we are proving? Could you just remind?
So we are now getting the topological Takens theorem from the main auxiliary theorem.
I see. Okay.
And we have already used very strongly the fact that we are finitely generated because we took this. Okay, so I argue that if P is too big, automatic. Right? Because in order to use the main auxiliary theorem, what I need to do is to verify condition star for all P. This is done. So I need to consider this. And the point is that 2D over R is exactly less than M. Right? Because I chose. Now note that if for X in XP it holds Fx equals Gx, then Gxp Gx, the cardinality of P, is by definition now this of course is containing all x whose the cardinality of the G orbit is exactly P. But this contains all x in x which have the property that fx is gx and fx has exactly size p. Because for such x, fx is the same as gx. And now, if we know, I claim that if we know for all x in xp that this holds, then this contains already xp, because xp are those x who determine p on f. In particular, the size of fx is exactly p. It's weaker, right? It's like losing information. It's only counting how many classes you have. So this small calculation wanted to show that if we can show this condition, we are done. Why is that? Because, okay, last step. It's missing last step. Dim xp is less than dim gx cardinality of p less than r over 2p. I remind you that in the topological Takens theorem, we have this assumption. And this calculation shows us that that actually xp is inside this set. So we have the same, and this is exactly, so I mean, this fact is exactly the fact that we need to verify in the auxiliary theorem.
So Yonatan, could you please repeat again the last line?
This one, yes? Or this one?
Is this the last one on the board? Yes.
So I didn't have space, so there is like 1, 2, 3, 4.
Oh, sorry. Here we have. What is it? Oh, XP.
I was trying to argue that xp is a subset of gx cardinality of p under the following condition. For all x in xp, fx is gx.
Essentially, under this condition, you can just there's no need to write containment. You can just write equality of these last two sets, right?
Yes.
This is the point.
Yes.
So the last containment always holds if you can erase fx equal gx.
To make the story short, we need to show for all x in xp that fx is gx. Which is interesting. It's like you see the whole orbit of x already in acting by f. Yes? And I don't know, maybe I can do it here. So let's take G, which is in G minus F. Now G, by definition, can be written like this. Right, where epsilon I is plus minus 1. Now the point is we want to take a minimal representation, minimal with respect to this L. If L is less or equal than M, then G is in, then there is nothing to do. We are not in this case. The point is that we can define the following. So it's like we take this G and we are acting on X. So first we take just the first element, that is the most right element, the one that when I is L. So it's S. I guess it's not the best notation here because I guess I need to write S and here it's like JI because each I chooses a certain generator. And the point is that I have here M terms and all of them are in Fx because all of this it's less or equal than M. But we know that Fx has size P, which is less than M, strictly less than M. So there are.
Sorry, so turn this. So you have a point X, and you.
What do you mean a point X? I have a point X in XP, right? Because I'm trying to show this. Yes?
Yes, and you kind of take orbit under partial.
Wait, what do I want to show? I want to show this, right? Do you agree with me that I need to consider just G which are not in F? I mean, if they are in F, there is nothing to prove.
No, right now I just trying to understand what is written on the board.
Yes, okay, yes, of course.
So you take point X and you take kind of partial orbit
under the representation of G.
G. So you take only the
First M term.
first. I see, and you just keep when you have repeated application of repeated generators. You just keep. You just take the powers.
Yes. Okay, you are right. Of course, I made a mistake here. This is not only plus minus one. It's actually, of course, if I have SI, I write it as S squared. Sorry.
So
no, because then no, because then I'm not in the plus. This is plus minus one.
Okay, okay. Now I see.
Yes, excuse me.
You don't skip.
I don't skip.
So once again.
So think it.
So you defined white.
I don't know. Let's say it was.
Okay, so let's.
I defined right.
Right. Fine.
The point is that the YT. Do you agree with me that they this term, excuse me, is inside BM0, right? Because there are only. And
so YTX is in Fx, sure.
yes, but we know this by assumptions.
Right.
But this is less than n. So there exists T such that YTX equals YT prime x.
Because here you took the last two covers. And now you can convert your bar.
So if there is a T equals T prime such that this enables me to write this shorter, so it's not a minimal representation, so
you just cut.
okay. So now the question is how to translate this in the Z case where everything is abelian. I think that it is the same.
But you also said one thing, and I was lost to listen.
Yes.
So at the very top over there, one of the obviously the outside inequality is the one what we need.
Yes.
The right hand inequality is. And assume that the right inequality was assumed in the topological Takens theorem.
Yes.
And I don't.
Yes, because if you remember when I wrote the topological Takens theorem, I didn't include the part which already appeared in the main theorem.
Okay. So it was here.
Yes.
Okay, yes. Okay. So no. Okay. So
You are right. And
I forgot that it was additional assumptions.
yeah, you must assume something on
Yes.
the periodic points.
Okay. Now it makes sense. Thank you.
Okay, so now let's
So here came to some conclusion. I missed
contradiction.
contradiction. So I.
Contradiction is with the minimality of the
representation.
I see.
Because we were able to.
Yes. Okay.
Okay, so now I want to prove the main auxiliary theorem, and so here let me maybe say some words about the what I call the combinatorics. Basically, we need to consider the product space x times x minus the diagonal. So let me, I will
Have already the definition of covering dimensional theorem?
it was here. But I erased it. But in a moment, in any case, we don't use that definition. We use something else that I will say.
You use it.
We define x triangle to be x times x minus the diagonal. And then we fix some compact set here. So and then we can define this. This is an idea that appears in all proofs of such theorems, that instead of considering all pairs, we consider pairs of points that belong to some compact subset inside this space x times x minus the diagonal. Minus the diagonal because we never compare a point to itself. We always compare a distinct point. And then the idea is to okay, it's easy to see that these sets are open, and the point is to show, to find a countable collections of Zi that covers this space, such that for all of them this is dense. And then we can use the Bell category theorem framework. That's the idea in all the proofs. And this is related actually to what I call the combinatorics of the orbit, because now you have 2 points. You have x1, and you have x2, and you have this finite f. And you start acting on x1, like in the previous picture, and then you can have, let's say, 2 very distinct cases. The first case is when x1 and x2 don't interact. we call that case non-intersective. And the second case is when they do interact. So for example, some element in f, when you apply to x2, equals some other element of x applied to x1. And the difficulty we had back in 2018 when we were thinking about, we were very modest. We were only trying to do the nilpotent case, right? We had zk, let's do the nilpotent case. We were not able to work with these combinatorics. Maybe it's possible, I'm not saying that not, but if you look at the proof for zk, you already see that it has more combinatorics than the case z, right? It's more complicated, and here it was even more complicated. And okay, so the idea, okay, so maybe here, because I don't have too much time, let me immediately now jump no, maybe this is not so. Okay, so maybe I do need to define what is coherence.
So Yonatan, so once again, Z, what kind of set is it?
It's a compact set living inside the product minus the diagonal.
Okay.
And as you can see in this set GFZ, okay, because when you want to show that a function is injective, you need to compare all distinct pairs. So here you do something weaker. You only compare the pairs that come from a set of pairs called Z. Okay? And then the task would be to find a good covering, right? Because if you can show that it works for all Zi in this covering, you're done. Because you have covered all possible pairs. So we now define something called a set is a set Z hat in its in the product is called F coherent if
So maybe still one question. So we were not discussing the proof of the main theorem.
main auxiliary.
Main auxiliary theorem. Okay, sure. Okay, fine. So we are assuming the main theorem, or
No, the order is that the main theorem is concluded from the main auxiliary theorem, and I did not tell you how.
Sure. Okay.
But that's actually, let's say that's not the heart of the proof. It's easy. And we also show that the main auxiliary theorem gives us the topological Takens theorem. So this, what I'm trying to say, this is the heart of the proof. This is what you need to understand how to prove. So a set Z is called F coherent if there exists a partition P hat or F hat, I will define this. So now we cannot work anymore with partitions of F. We need to work with partitions of two copies of F because we have two elements. So F hat is, just think about it like this. It's two copies of F. This is F hat. So I don't know, let's say that F, somehow we have numbered it. So we have like 1, 1, 2, 1, until 5, 1, and here we have 1, 2, 2, 2, 5, 2. And what we want to do is, if there exists a partition of F such that Z hat is inside its diagonal P hat, which is by definition for every x1, x2 in Z hat, the partition determined by F hat is P hat. Okay, so how do I act? How do I act with F hat on X triangle. So the action is, so I have like this. I fix an element in f hat. Now an element in f hat is an element in f that has an additional index, first floor or second floor. If I'm in the first floor, I'm acting on the first element. If I'm in the second floor, I'm acting on the second element. So in other words, this is just tailored to understand such pictures. Because in a sense, I have elements of f, and I want to have a system where I know how it acts on x1 and how it acts on x2. So I just write it in two floors, in two rows. And then...
so you consider f hat as a subset in some group, or just...
So as I said, f hat is just two copies of f. F was this finite set in G.
So you consider space.
No, union of two disjoint copies.
Union of two disjoint copies, exactly. It's not a product, it's a union.
Yes. I just thought first exemplar.
Yeah, I was asking because previously when you had space xp, you had action of some group on x, some subset in partition p, and here do you assume that you act on x delta by g times g, or you just...
Well, first of all, obviously you do have an action. You can consider if you want the g times g action, but it's not what I'm doing. I think that at this stage of the proof, it's better to forget of the dynamics because the set f is fixed.
Okay.
So just think about it. I took two copies, and
I don't understand the statement because p hat is a partition, right? So what
of
is
this set.
Sure.
For example, it looks like this.
Fine, but what is the left hand side?
So here I'm using a notation that I haven't used, but I said it. I said it. So just as in the previous case, a pair determines a partition. You fix x1, x2, then you have the action of f hat on it. And the question is, does the partition you get, does it equal p hat or not? So we say that a set is called f coherent if it consists only of pairs who give a specific partition. One. And two, if p hat I will give you an example, but let me write the condition. So the point is that we want the following fact, that if we know that all x have the same behavior under these two copies of f, and in addition, if we know that two elements are not in the same partition element, then when we act with these two different elements on the z hat, but I remind you that acting on z hat here is either acting on the first coordinate or on the second coordinate, we get disjointness. Let me give an example which I think will clarify it. Maybe I should say that the proof proceeds to showing that you can cover X triangle by F coherent sets.
By
F coherent sets, so by compact sets that have this additional property. So now I have only 15 minutes, so I'll give the example and then I'll say something about which definition of dimension we use. So let's say that Z acts on X, and let A B consist of X in X whose have the following, that X, 2X, so they are of order 3. X, 2X, 3X, and then we go back.
What is X?
So A, let me draw it. So this is set A, and then we act with our generator. So with the T is the generator of Z. Here we get another copy TA. Here we get T square A. And then we go back. So this is a very specific set of elements, this A, that have this property. They have exactly order 3. Now I want to consider the following set. Z hat is the pairs X, Tx for X in A. This is clearly living inside X triangle, right? Because we know that A and TA are disjoint. And I'm going to take F to be these 3 elements inside the group. And now I want to understand which partition, so I have, where did I write it? So I have some pair of points x1, x2 inside of Z, and I want to understand which partition it creates on 2 copies of F. So I wrote it like this. And then we see that this is one element, this is one element, and this is one element. Now, I also claim that this set is the okay, so that's good. It means that all of X inside of Z hat create the same partition. Moreover, I claim the second condition holds, in the sense that if I consider 2 elements that are not in the same partition element, and I act with the corresponding copies of F, then I get a disjoint. Because, for example, here I get A, because it's the identity, and here I get TA. And as we assume that A and TA are disjoint. Okay, so the theorem is to show that you can write triangle as a union of compact F coherent sets. And then the next part is to show that when you have a F coherent set, then indeed GF, this coherent set is dense. And now I want to mention Ostrand's theorem from 65. So Ostrand theorem is actually a characterization of covering dimension. So dim x is less than n if and only if for every epsilon and for every k bigger than 0 there exist n plus k families C1 up to Cn plus k of pairwise disjoint closed sets such that for every d in Ci for all I, the diameter of d is small, and to the order, oh, maybe it's better to write like this because to any n distinct members of C1 up to Cn plus k cover X. So it's like you get n plus k families of closed set, and the point is that each one of these families, they are constitute of disjoint closed sets. On the other hand, they have small, okay, in addition, all of them have small diameter, and key property, taking any n out of this C1 up to Cn plus k, you get a cover. And I don't have time to discuss it. Ostrand's theorem has two directions, of course, because it's if and only if. One direction is easy, and the second direction is hard. The direction which is hard is to start with the original definition and to construct these sets. Why is this? Okay, so I was going to show to you on the example that we discussed how we use Ostrand's theorem. This is actually a major simplification of the theorem because obviously this set is a very simple set, but this case already demonstrates the point that I was making in the beginning, that Ostrand theorem is useful here in the sense because it allows you to perturb on these disjoint families. So first of all, I have 5 minutes, so I'm trying to think what I can say. Let me see. I can start writing here. assume that the dimension of in the example the dimension of A is 1, and I choose in Ostrand theorem n equals 2 and k equals 1. Thus, in A, we find 3 families of pairwise disjoint closed sets with small diameter. And here is the key point, such that each x in A is contained in at least 2 sets in the family. Right? Because if we know that the second condition tells us that any 2 elements from C1, C2, C3 covers X. So if there is an X which is only contained in C3, this is immediately a contradiction, right? Because then C1 and C2 do not cover. So each X must be contained in at least 2. Okay, so how does, now A is one-dimensional. Let's assume that A is an interval. So we need to find 3 families of pairwise disjoint closed sets such that each element is contained. So I drew it, I did the following picture. First family, I took this interval and this interval. Each family is a family of disjoint closed sets. So the first family is this and this. The second family is this, and this is one element. And the third family is this and this and this. Now you need to check that every element is covered by 2 elements. Now this looks like the diameter is big, but of course we can do the same idea with very small.
I don't understand the picture at all. So we have inside one-dimensional segment. So you're
the theorem, Ostrand's theorem, claims that dimension of segment is less than 2. If and only if, for every k in particular 1, there exist 3 families of pairwise disjoint closed sets such that they have small diameter and any 2 distinct members cover X. Or, as I translated it, any X is contained in at least 2 members. So I found 3 families. Each family consists of 2 well, maybe it's better to think about it on the circle if you want. I want to say that each family contains 2 intervals, so this is connected, let's say. And I need to do it, I need on one hand to keep the disjointness, but I need to have the covering of order 2. Does it make sense or not?
sorry. So we are on a segment.
Yes.
So how come this picture represents something on the segment that you don't understand?
The idea was like to say that this is family 2. Okay, you're right. Maybe it's better with colors. You're right. Let me do it.
Oh, I see. Now I see. So
I didn't have color in my notes,
okay.
but here I can do it.
Okay, I see.
So the first family will be white. The second family.
I see.
Yeah, this makes
It's better.
Yeah.
Okay, so I'm out of time, but now the last part of the talk was so what I wanted actually to show to you was that for this particular Z, the GF with this particular F is dense. So I was going to start with some function F and I was going to perturb it. And in my perturbation, I was going to use these three families. Well, the key point would be that to perturb on a disjoint family of closed set is very easy. Because remember, actually, it's I don't have two segments, I have many segments because I need them to be very small. And then what I do actually is in the proof, I will on each one of the segments I give a fixed value. But okay, this I guess it's not clear saying it so fast. But I don't have time, so thank you very much.
Any questions?
I still have as you told us, so essentially the idea of the proof, as I understand, is that you have this notion of F-coherent sets, and you have to show that they cover the whole space, and then you have to show, and you can find a countable collection which covers the whole space. And then the next thing is that you have to prove that these sets GFZ are non-empty and dense.
Dense, yes.
Right? So from what you were telling us, this Ostrands theorem comes in the second part.
Yes.
And the first part?
That's no problem.
That's okay.
Yeah,
that's
because basically you just say, let's say it's just what Artem said. Each x must determine some p on f, right?
Right.
So
okay.
and then we have, okay, we want them to be compact because you know this x triangle is not a compact set, right? But okay.
And the next short question is, so does this reformulation of the covering dimension, has it also appeared in your work before?
No.
Or this is something?
No, that's the whole point. That's the new input that enabled us to do it in the more general
But there are some new ideas on the combinatorics of finite.
You can, this is available in archive, you can check out the combinatorics. I wouldn't say it's more hands-on. But if you understand the proof, you immediately see that the key point is that you can perturb on these disjoint families, which I didn't discuss how we did it before, but before we were actually, maybe this also I should have said that, before that we really reduced it to linear algebra, so we had these matrices. And we had some conditions on matrices coming from the combinatorics. And at one step, it was too complicated. Whereas here, in Ostrands theorem, there are no matrices because these families are disjoint. There is no linear algebra in some sense.
So do you think this can be extended to the Lipschitz category?
Lipschitz category, so what would that be?
So I guess, finite dimensional subset in RD with bounds on the box counting dimension and maybe a group acting by Lipschitz maps. And you look at typical Lipschitz observables.
Right. Because
maybe
we know the equivalent theorem of Menger Nöbeling.
Exactly, which is Mania's theorem, I guess, for Lipschitz, in the Lipschitz case.
So I guess my question would be then, what is the
analog of
Ostrands theorem for box covering dimension? By the way, this is very interesting history because if you look up the paper of Ostrand, this is a quite known paper because his paper is in the context of Hilbert Sertin's problem.
Hilbert what?
Sertin's problem. The one when you want to write a multi-variable function as a sum of functions is
I have one more question.
Yes, of course.
So, if instead of an equivariant embedding, let's say in this first main theorem, you just want to say that for typical f, you get a factor map instead of injective map, just something equivariant. Do you think that you can get rid then of this condition on the on periodic orbits, so to say?
But I don't understand the question. The orbit map is always an equivalent factor map, right? By definition.
Because it goes to the infinite, to the whole group.
Yes, yes.
Okay. So maybe then in the Takens case, with this existence of the prediction map.
But what in the Takens theorem there is no factor notion.
Because there is no dynamics downstairs a priori. But if you ask whether there exists, let's say, a continuous dynamics. Okay, maybe I should think. Maybe in the group setting it doesn't make sense.
Or maybe we did, because I didn't.
Yeah, but I want to have for typical observable.
Yeah.
For typical observable, you want what in the Takens theorem? That the f acts?
Well, that you get that your diagram commutes just on this part, on this finite part. But maybe it's a wrong question in this generality.
So it's a question about defining a completely new dynamics on this actually cube.
Just predictability. Action of arbitrary group.
Right. Okay, so this is easier. You are actually okay. So you are asking if generically if we can have the condition f of x equals x2, then for maybe let's call this observable h. Then for all f in f, you want that this should hold. Yes?
I guess maybe first condition is not just on h, but on this h with index f. So you look at the whole.
Yes.
At the whole
yes.
image.
Yes.
Yes.
Is this a generic?
Probably. I'm okay.
This I need to think a priori. I cannot rule it out. So, okay, so here there is no F. No, there is, because you want to.
Yes, you want to act by something.
You want to act. Okay, this I need to think. And the idea is, of course, to get rid then of the condition. So
The
no condition
of
at all.
Well, maybe just finite dimensional.
Maybe only finite dimension. That's an interesting question. Okay.
Yes, do you need a metric on it?
Yes, we work with the. I mean, in
because
all.
when you took neighborhoods on diagonal, I thought about uniform spaces.
Actually, Ostran's theorem was proven without. I mean, there is a version, you can find it in Engelking's book. So probably everything works without the metric, but we like to work with the metric because it's easier. What? Yeah.
Any other questions? Or maybe online? Okay. Thank you very much.
Christian.
Yes?
Yes, I was even thinking of proposing having a mini course on this or something.